So when you really think about it, the single biggest challenge facing these highly specialized AI agents today,
The ones that are actually writing code with us.
exactly, the ones we rely on to write, debug, refactor our code,
Mm.
it isn't really their lack of ability, in the moment.
No, not at all. Their short-term context windows are immense. They can hold a huge amount of data.
But that's the key, isn't it? Short term. The moment that session ends, poof, it's
Yeah.
all gone.
All of it, all that nuanced, hard-won knowledge about your project's specific architecture, the weird bugs you fixed last week, the technical debt you're trying to manage, it just evaporates.
We are grappling with, well, a pervasive issue of AI amnesia.
It's the fundamental problem of statelessness. And you're applying it to a process software development that is deeply stateful. It's all about history and context.
Right. So every new interaction is basically a cold start.
A total cold start. The large language model, the LLM, is forced to waste precious time, and this is critical, expensive tokens, just rereading foundational information.
Reindexing files, redriving conclusions, it already figured out.
Exactly. Last week's work is just gone from its active memory. For any kind of iterative development where that continuity is the bedrock of productivity, this stateless approach is profoundly painful.
So, okay, the question becomes, how do we fix this?
Mm-hmm.
What if we could give a tool, something like Claude Code, a genuine, persistent, long-term memory?
And not just a simple log file.
No, I'm not talking about just dumping a massive chat history into a searchable text file.
Right.
We need something intelligent, token efficient.
Something that automatically captures the important stuff.
Right, the high signal context, and then compresses it down to its essential lessons. And then, and this is the magic part, surgically injects it back only when the agent specifically needs that piece of historical knowledge.
That is precisely the ambition of the source material we have just immersed ourselves in for this deep dive.
Okay, so what have we been looking at?
We've been analyzing the technical documentation, the configuration files, and really digging into the underlying GitHub repository for a plugin called Claude-Mem.
Claude-Mem.
And it's a specialized plugin engineered specifically to provide Claude Code with that crucial persistent memory layer. And wow, the material it's dense. It gets into everything from hybrid database architecture to some pretty advanced token optimization strategies.
So our mission for you, the learner, is to synthesize all of this complexity. We're going to extract the core insights, both technical and strategic.
Mm-hmm.
We need to define what Claude-Mem actually is, understand the sophisticated ways it's using these multiple databases and AI compression to solve that fundamental memory problem.
And crucially, how all those engineering choices translate into tangible benefits, saving developers time and, of course, preserving that all-important token budget.
We're basically watching LLMs evolve from just being these high-powered transactional tools
To becoming genuine collaborators that have accrued, engineered knowledge.
Okay, let's unpack this, starting with the fundamental system that's designed to stop a large language model from forgetting what it did last week and start acting like a truly knowledgeable long-term partner.
So at its highest level, its highest conceptual level, Claude-Mem is really defined by its ambition for autonomy.
Autonomy.
It functions as a specialized Claude Code plugin that just runs constantly, quietly in the background. Its primary job is the automatic capture of every consequential interaction the agent takes.
So it's turning the ephemeral nature of a coding session into a permanent, searchable historical record.
Exactly.
Okay, so it's like a tireless digital biographer for the AI agent. The documentation describes this very specific three-part mechanism: capture, compress, and inject. That's how it achieves this continuity.
Mm-hmm.
But let's talk about what gets captured. They really emphasize tool usage observations. Why that specifically? Why not just record every single line of the conversation?
That is a critical design choice, and it's all rooted in efficiency. Tool usage observations are the highest signal moments. They represent genuine, meaningful work when the Claude agent decides to interact with the environment.
Like reading a file or running a terminal command.
Or performing a Git operation or modifying a block of code. That action is a concrete, non-negotiable step in the project's evolution. By focusing on those points, the system captures actionable intelligence.
So it's about intent and outcome.
Precisely. It filters out all the noise of the agent's internal monologue or the planning discussions or just the simple back and forth with the human developer. It captures the results of the agent's planning, not the planning itself.
That makes perfect sense for efficiency. Okay, so once those high signal observations are captured, we get to step 2, compress.
Right.
This is where it gets a bit meta, because the AI is using itself to summarize its own work. The source material explains that it uses AI, specifically the Claude agent SDK, to generate what they call semantic summaries.
And this step is the key. It's what enables the entire token saving strategy. A raw observation can be huge.
Oh yeah, think about the output of a long terminal command, or a stack trace from some complex error.
Or the full content of a big config file before and after a change. If you just stored that raw data, trying to retrieve it later would be immediately token prohibitive.
You'd burn through your budget in a heartbeat.
Right. So the AI compression step reduces all that raw data into a concise semantic summary, a brief but really rich natural language description of what was accomplished and what the significance of that action was.
And that compact summary is what actually gets indexed and stored in the long-term memory.
Which makes future retrieval incredibly fast and, more importantly, low cost.
Which brings us to the final step, inject. So you have this compressed, relevant context. How does the system pull it back into a future session without just, dumping a bunch of irrelevant data?
So the injection process is entirely prompt-driven or session-based. When a new session starts, or when you submit a new prompt that continues a previous task, Claude-Mem uses a suite of really sophisticated search tools to query its permanent store.
And we're going to get into those tools later.
Oh, yeah. And it retrieves only the most semantically and contextually relevant summaries based on the current context, the files you're looking at, or your immediate request.
And then it just injects that context back into the LLM's working memory.
Effectively and efficiently reminding the agent of past similar tasks or previous bug resolutions or established code structures, all without the cost of rereading weeks of transcripts.
The benefit here, this continuity, it's transformative. It completely shifts the AI agent's role. It goes from being this high-powered but ultimately transactional thing, ask a question, get an answer, start over next week,
Right.
to being a genuine collaborative partner that actually maintains a persistent awareness of the project's history and state.
And the system's design really emphasizes that this is all seamless and automatic. Zero manual tagging or intervention from the developer.
The developer experience is the priority.
Absolutely. The developer shouldn't have to manage the memory. The system just observes the agent's output behavior, which is the most reliable source of project context. This transforms Claude from just a stateless computational engine into a knowledge-aware entity.
An entity that possesses institutional knowledge. It understands the project's accumulated technical debt, its architectural choices, the specific history of bug fixes.
Yeah.
Let's expand on that difference between the context window and this kind of engineered memory.
Yeah.
Because we're seeing these LLM context windows ballooning, 200,000, 500,000 tokens, which sounds massive.
And it is massive, but as you said, it's only short-term volatile memory.
Okay, so give us an analogy.
Think of it using the classic computer analogy.
Right.
RAM versus a persistent hard drive.
Okay.
That massive context window, the 500,000 tokens, that's your super fast RAM. It holds all the immediate inputs, the files currently open, the conversation flow right now.
But when the power goes off or the session closes,
The RAM is wiped clean. That's why it's called short-term memory.
knowledge retention is volatile.
Exactly. Claude-Mem, on the other hand, provides the long-term persistent memory. That's the hard drive. It stores synthesized essential knowledge that survives those power cycles.
And crucially, because it uses AI compression, it's not just storing raw data. It's not a massive unindexed file dump.
No, it's storing lessons learned, all indexed for rapid semantic retrieval.
So if Claude spent, say, 3 hours tracking down some bizarre caching issue last month, that entire experience isn't lost.
It's not lost. It's stored as a dense, high-value summary. Something like implemented TTL cache and validation logic for service X due to race condition, complete with the context of success.
And that's a knowledge graph built on actual agent actions.
Precisely. So if a new similar caching bug pops up, that learned skill, that compressed summary, can be instantly retrieved. This completely avoids the token cost of having to feed the agent the entire 3 hours of debugging transcripts from last month.
This mechanism, it just dramatically changes the economics of using AI for coding, doesn't it?
It ensures that the work done in one session builds upon, rather than just repeats, the work of the past. It provides the foundation for, well, true lifelong learning in an AI coding agent.
The fact that this memory is persistent and smart implies a pretty sophisticated structure underneath it all. This is clearly not just a single CSV file somewhere.
No, not at all. The system relies on a hybrid architecture, and it's
Hmm.
designed specifically for rapid context retrieval and, critically, for token efficiency.
Okay, so that hybrid design is the architectural signature.
It is. And the core philosophy that guides how they manage and deliver that context is a concept known as progressive disclosure.
Progressive disclosure. Okay, I know that term from UI design. It means you only show the user what they need when they need it to avoid overwhelming them.
Right.
So how does that translate to an LLM memory system?
It translates directly to managing the token load. The retrieval process is rigorously layered. The system is engineered to never, ever dump massive amounts of data into the prompt immediately.
So it's not just a fire hose of information.
No, it retrieves only a compact index first. Then, if required, the surrounding chronological context. And only finally, the full, most token-expensive details.
And only when the LLM explicitly signals that those details are necessary for the task at hand.
Exactly. It's context priming executed with a surgical level of control. The documentation even notes that token cost visibility is a feature.
What does that mean?
It means the agent's own decision-making process is informed by the relative expense of retrieving specific layers of memory. It knows which actions are cheap and which are expensive.
That meta-awareness of cost,
Yeah.
that's really innovative. Okay, let's look at the actual components that power this layered retrieval, starting with the heart of the system, the worker service.
A worker service is the backbone. It runs as an HTTP API, it manages all the persistent memory operations, and it handles the database connections. And importantly, the documentation notes a recent architectural choice. The service is managed by the Bun JavaScript runtime and process manager.
Okay, this is an important detail for performance nerds out there. They note a migration in version 7.1.0 from PM2 to native Bun management. Why is that significant for a persistent background service like this? I mean, why Bun and not the more established Node.js?
That choice, it just signals a real dedication to performance and resource efficiency. Bun, as a modern runtime, is significantly faster than Node.js, especially in cold start times and overall execution speed.
Right.
So for a persistent worker service that needs to be constantly running and ready to handle memory requests with minimal latency, even after a reboot or a session ends, Bun offers two crucial advantages.
Which are?
A lower memory footprint and superior concurrency handling. For a plugin that's running alongside a heavy code editor and an LLM, maximizing resource efficiency is paramount to system stability.
So it's about making the memory engine feel instantaneous and minimizing its strain on your system.
Exactly.
And while Bun is a key requirement, the system installation cleverly handles this. It auto-installs Bun if it detects it's missing during setup.
Absolutely. So this worker service operates on port 37777,
Okay.
and that port is the system's external interface. It provides the internal API for memory search, but it also hosts a crucial feature, the web viewer UI.
A web viewer UI accessible through that port, so developers can actually look inside the AI's memory.
It provides essential transparency. A developer can log into that interface and see the real-time memory stream, the raw observations being captured, the resulting semantic summaries, and how the data is being indexed.
So it turns the AI's internal memory process from a theoretical black box.
Into a completely transparent, searchable audit trail. On top of that, the API exposes 10 distinct search endpoints, which really illustrates the complexity of how different types of context can be retrieved.
Whether it's chronological, project-specific, or keyword-driven.
Right?
Okay, let's pivot to the databases, because this is where the speed and the intelligence of the retrieval really take shape. They're using a hybrid search strategy.
The system relies on two distinct databases working in concert.
So what's the first one?
We start with the persistence layer, Scolate 3. It's bundled with the plugin, and it serves as the robust, reliable storage for all the sessions, the raw observations, and those compressed summaries. But they've optimized this significantly by using the FTS5 extension.
FTS5 Full Text Search version 5. I'm going to linger on this for a second. Why is optimizing for full text search so critical in the context of persistent code history?
That's where the performance advantage for developers lies. If you used standard SQL indexing on these massive text fields, searching for arbitrary keywords or code snippets or error messages across thousands of past observations would be incredibly slow.
A real bottleneck.
A huge one. FTS5, however, pre-indexes all the tokens within those text fields. This means when the LLM needs to find a memory entry based on fuzzy, high-velocity keyword searches,
Like searching for that weird Lambda function signature in the legacy service.
or the specific UAUID I used in the test mock last Tuesday, FTS5 makes that search instantaneous. It provides excellent deterministic retrieval.
So FTS5 handles the traditional exact match or keyword-based search with incredible speed.
Precisely. But modern knowledge retrieval demands more than that. It demands semantic understanding. And that's where the second component comes in, the Chroma vector database.
Chroma. Okay, so it operates alongside SQLite, and it specifically enables this hybrid semantic plus keyword search.
All right.
So this is the mechanism that lets the system move beyond finding exact words and start finding concepts and ideas that are related, even if the phrasing is completely different.
This hybrid approach is what makes the memory truly intelligent. Those compressed semantic summaries we talked about, they're converted into vector embeddings, numerical representations of their meaning.
And Chroma indexes those vectors.
It does. So if a developer prompts, hey, I need to remember the solution we implemented for that database contention issue we had last month, the FTS5 search might pull up entries with database and issue.
So the keywords.
But the semantic search via Chroma will also retrieve entries related to optimistic locking or transaction rollback or connection pooling, even if those specific phrases weren't in the original query at all.
Wow, that dramatically increases the likelihood of finding the most relevant, high-quality context.
It really does.
And again, this sophisticated integration of a Python-based vector database is made seamless because the installer automatically manages the necessary dependency using the UV package manager.
It's abstraction mastery. The user gets a hybrid performance system without having to manually manage a complex multi-language dependency stack.
Okay, let's talk about the lifecycle hooks. These are the tripwires that actually trigger the capture of memory. The system uses 5 core hooks. What are they and why these specific moments?
These 5 hooks are chosen because they encapsulate the critical moments when new knowledge is acquired or context is needed in an AI agent cycle.
So what's first?
First is session start. This is the opening trigger. It's essential because it allows the system to inject relevant context before the agent even sees the first user prompt. It establishes the context for the whole session.
Okay, that makes sense. Priming the pump.
Then you have user prompt submit. When the developer gives a new instruction, this is the chance for the system to do a targeted memory search based on that newly stated intent.
So the agent gets relevant past knowledge immediately.
Third, and this is the most critical capture point, is post-tool use. After the agent successfully executes a tool, runs a test, writes a file, the system captures that output observation. This is when new verified knowledge is generated.
It's the core of the long-term memory.
Exactly. Then there's stop, when the agent concludes a complex thought process or reaches a natural stopping point. This serves as a boundary marker, often triggering an internal summary of what just happened.
And finally,
Session end. The agent is shutting down. This is the final, crucial opportunity for comprehensive summarization and compression, making sure everything is persisted and indexed before the worker service might be idled.
so memory capture is entirely deterministic. It's tied directly to moments of high informational value.
Yes. And the sources also briefly mention a smart install prehook.
What does that do?
The smart install hook is the system's self-reliance feature. It runs before the main session starts and performs cache dependency checking. It automatically verifies that Bun, SQLite, and URV are correctly installed and up to date.
So it makes the whole setup robust against environmental changes.
It ensures the persistent memory service is always ready to go.
And to wrap up the architecture, the sources highlight this evolution of efficiency. Beyond the migration to Bun, a shift in version 5.4.0 plus from older tools to skill-based search resulted in, what, 2,250 tokens saved per session?
Yeah, a substantial saving, around 2,250 tokens per session.
That's not just a technical improvement, that's an economic transformation.
It absolutely is. It indicates that the previous mechanism for retrieving context was far too verbose. By transitioning to a more refined, skill-based retrieval mechanism, the agent can access its memory using a drastically lower number of tokens to get the same, or even better, quality of context.
So they optimize the prompting interface itself.
Exactly. It proves that in this LLM world, engineering prompt efficiency is just as critical as engineering code efficiency.
That focus on economic optimization brings us directly to, well, what I think is the genius mechanism designed to protect the developer's wallet. The 3-layer workflow pattern. The problem, as you mentioned, is the high token cost of just fetching the full observation details, the code diffs, the verbose logs, for every single search query.
And this workflow is the precise solution to that pain point. It embodies that progressive disclosure strategy we discussed, and it results in an estimated roughly 10x token savings
10x.
by ensuring that full details are only fetched after rigorous filtering. The system actively constrains the LLM to follow this token-efficient path.
Okay, let's walk through the pattern layer by layer. Let's see how the agent is guided through this.
All right, layer 1 is search. When the LLM gets a prompt that requires past context, its very first action has to be using this dedicated search tool.
And what does that do?
This tool queries the persistent memory, that hybrid search layer, and it rapidly returns a very compact, high-level index of results.
So what's in that index, and why is it so cheap?
The index just contains titles, observation IDs, dates, and those brief semantic summaries. The results of the AI compression. And they're cheap, costing only about 50 to 100 tokens per result.
So this layer is the initial filter.
Exactly. It leverages the speed of FTS5 and Chroma to prune the vast memory store based on your query, the type of observation, the date range, and the project context. It quickly establishes a pool of potentially relevant historical events.
It's like the table of contents view. It lets the agent grasp the scope of relevant memories without having to read the whole book.
A perfect analogy. Once the agent has that compact index, it moves to layer 2 timeline.
The timeline tool.
This is the context checker. It's used to view the immediate chronological context surrounding a specific observation ID that the LLM has flagged as interesting from that first search.
But it doesn't fetch the full details yet.
No, not the full details. It just gets the events that happen immediately before and immediately after that specific ID.
And why is that surrounding chronological context so vital before you do the expensive retrieval?
Because relevance is temporal. An observation ID might show that the agent implemented a specific fix for a dependency, but the timeline tool tells the agent, did the user immediately revert that change? Did the agent run a test right afterward that failed? The surrounding context provides the necessary narrative integrity to understand the true success or failure of that original observation.
So it prevents the agent from spending 1,000 tokens fetching the details of a fix that was immediately undone.
Precisely. It's the moment the agent confirms that memory nugget is actually applicable and useful.
Okay, so we've filtered down the entire memory database in layer 1, and layer 2, we've validated the context and consequence of those few promising entries. Only then do we authorize the expense in layer 3, get observations.
This is the critical retrieval layer, and this is where the tokens are spent. It fetches the full, verbose details, the raw logs, the extensive code diffs, the terminal output, everything necessary for the agent to replicate or understand the solution.
And these details are expensive.
They are, ranging from 500 to 1,000 tokens per result. But because Claude-Mem enforces the rule that the agent must use this tool only for IDs that have been rigorously filtered and validated across the previous 2 layers, the expense is highly justified and minimized.
That tiered approach is what makes that 10x token saving estimate entirely plausible. It turns retrieval from like a broad fishing expedition into a surgical extraction. But the central question here is control. How do you ensure the LLM, which is inherently creative and adaptive, actually sticks to this multi-step protocol? Couldn't the model just decide to skip layers 1 and 2 and call get to observations immediately?
That is a fantastic question, and it's precisely why the system provides 4 MCP, model-controlled program, search tools. And it's why the 4th one is so fascinating.
Okay, what are they?
The 4 tools are search, timeline, and get observations, with the explicit instruction in its description to always batch multiple IDs to maximize efficiency.
And the 4th one?
The 4th tool is important.
Important. Okay, let's dive deep into that. It's not a search tool. The documentation calls it workflow documentation that is always visible to Claude. Explain what that means.
Important is not documentation in the way you and I think about it. It functions as a persistent, high-priority system prompt injection.
Oh, okay.
It is a mandatory meta tool that guarantees adherence to the token-saving workflow. When the agent starts, this critical workflow guide is injected into the highest context layer. It serves as an internal, non-negotiable constraint on the LLM's behavior.
So it's perpetually reminding the agent of the cost-saving mandate.
Yes. It's basically saying, do not fetch full details unless you have filtered and contextualized them first using the 3-layer pattern.
So it's like the LLM's digital conscience. It's an ever-present sticky note that dictates cost-efficient behavior, ensuring the agent uses its memory intelligently rather than impulsively.
It creates a self-regulating, economically optimized agent. If Claude deviates from the workflow, the presence of that important directive will likely result in the agent self-correcting.
Wow. Okay, beyond the workflow, let's touch on some auxiliary features that enhance this. First, citations.
Citations provide crucial accountability and auditability. Since every past observation is stored and referenceable via a specific ID, when Claude uses that memory to generate new code or resolve a bug, it can output the specific ID it used.
Which allows the developer to verify the source of the AI's knowledge.
And that verification is simple. The developer can just access the cited memory directly via the Worker Service API, so http://localhost.3777777 API observation.
Which turns the AI's memory application into a completely verifiable source of project truth.
It connects the theoretical application of knowledge back to a concrete, time-stamped action that took place. It builds trust.
We also need to talk about privacy control. In any dev environment, sensitive data is a constant concern.
Security is addressed directly through the use of private tags. Developers can wrap sensitive inputs or outputs like temporary API keys or proprietary algorithms within these tags.
And the system knows to ignore that content.
It's designed to exclude any content within those tags from being stored in the persistent memory database. The note about supporting a dual-tag privacy system since version 7.0.0 plus suggests even more robust and granular control over confidentiality.
And finally, let's look to the future, which is hinted at with the beta features.
The existence of the beta channel and experimental features like endless mode shows the project is actively looking ahead.
Endless mode. It's described as a biomimetic memory architecture for extended sessions. What do you think that means?
Well, if the current system models the transfer of short-term to long-term memory, endless mode is likely tackling the problem of continuous adaptive learning over massive time spans. It's probably mimicking biological consolidation and pruning of memory.
So it's constantly refining and prioritizing the most essential context.
I think so. It would allow for truly enormous continuous sessions without the typical token overload. It's the ultimate vision of a coding agent that never stops learning and never incurs the penalty of having to carry every single historical detail with it.
So for the learner out there who's interested in adopting this highly optimized system, how complex is the deployment? I mean, given the list of requirements, buns, SQLite, chroma, specific hooks, you might expect a massive dependency headache.
You might. But the Quick Start Guide suggests a path of extreme simplification.
How so?
The power of the plugin marketplace model is the complete abstraction of that complexity. The entire process is boiled down to two simple commands that you execute through the Claude Code plugin interface.
Just two commands.
First, plugin marketplace add the .Claude-Mem, and second, plugin install Claude-Mem. That's it.
So what's happening automatically behind those two commands that makes the installation so frictionless?
The automation sequence is pretty thorough. It handles downloading pre-built binaries, so no messy local compilation.
Okay.
It handles dependency resolution, so it installs all the required external dependencies, including checking for and installing bun and the Python package manager UV for Chroma.
If they're absent.
If they're absent, it configures all the necessary lifecycle hooks, and it automatically starts the core worker service upon the first hook trigger in a new session.
So the persistent memory engine is online exactly when you need it.
It's a complete end-to-end, batteries included approach, which is essential for a tool that's designed to reduce friction.
We should still be clear about the system requirements checklist, though.
Yep.
Even if they're auto-installed, what are the crucial dependencies the system relies on?
To run the plugin, the core host environment needs Node.js version 18.0.0 or higher,
Okay,
the latest version of Claude Code with active plugin support,
of course.
and then the auto-installed stuff, Bun, the JavaScript runtime, SQLite 3, which is bundled, and Juve, the Python package manager for the vector search.
So it really does manage that complexity of integrating components across different language ecosystems. Now, where does this persistent memory actually live on your machine, and how do you configure it?
By default, the entire persistent memory store, the database, logs, configuration, is all housed within the developer's home directory under .Claude-Mem.
Okay, so as a developer, you need to know where the levers are. What are the key files in that directory we should know about?
There are three main ones. First, claude-mem.db. This is the heart of it, the SQLite 3 database with the entire history.
Got it.
Second, settings.json. This is the configuration powerhouse. It's auto-created on the first run, and it allows for fine-grained control over the system.
And third?
Third is logsworker-yyyy-mm-dd.log. essential for any troubleshooting. It's a detailed audit trail of the worker services operations.
Okay, that settings.json file dictates behavior. What kind of things can you tune in there?
You can customize the AI model choice used for summarization, the specific worker port in case of conflicts, the log-level granularity, and critically, you can fine-tune the context injection settings.
So you can adjust how aggressively or conservatively context is pulled back into the prompt.
Exactly. You can balance token cost against retrieval completeness based on what your project needs.
And for environments where the default location isn't suitable, I assume there's an override mechanism.
Yes. For developers using custom environments like containers or network-attached storage, the data directory can be overridden using the environment variable Claude-Mem. It's very flexible.
So once it's installed, how do you actually confirm that this sophisticated hybrid memory system is working? How do you verify it?
To verify the fundamental plumbing, you can check the hook configuration file, .cat, plug in hookshooks.json.
Okay.
To confirm the persistent memory engine itself, the worker service is alive and well on port 37777. You run npm run worker.logs. That gives you the real-time status.
And the ultimate proof of function, the memory retrieval check.
That's handled by a specialized test command, ntm run test.context. This command executes an end-to-end verification. It makes sure the system can write context, store it, and then retrieve it accurately.
So it confirms the entire stack is functional.
From the agent hook all the way to the database retrieval.
What's really unique here, though, is the troubleshooting approach. The source mentions a troubleshoot skill.
Yeah, this is pretty cool. If you run into an issue, you just describe the problem naturally to Claude. The system includes a dedicated troubleshoot skill.
So the agent diagnoses itself.
It does. The skill allows the agent to automatically diagnose the described issue using internal system checks and its knowledge of common failure points, and then it provides immediate, actionable fixes right there in the chat interface.
The AI helps debug its own memory system. That's its recursive resilience.
And if the issue requires external help, there's an automated command, npm run bug report. This command aggregates all the necessary diagnostics into a clean, comprehensive package, saving you a ton of time.
And upgrades are handled automatically through the marketplace.
Seamlessly, which is essential given the pace of these efficiency improvements.
This level of architectural complexity and efficiency improvement, it really speaks to a dedicated, high-quality development effort. So let's shift our focus a bit to the surrounding context. The community building this tool, and, critically, the legal framework that governs its use.
The project, which is led by Alex Newman, has garnered substantial community attention, and that really reflects its technical merit and, frankly, the necessity for this in the AI agent space.
The metrics are impressive.
They are. We're talking 12,000 stars, 753 forks, and a substantial history of continuous improvement with contributions from 18 different developers. It's highly regarded and widely monitored.
And the tech stack is intentionally modern, built with the Claude Agent SDK, powered by Claude Code, and written mostly in TypeScript.
Right, which ensures type safety and scalability. And the contribution workflow is very standard and encourages continued iteration. It's a healthy, well-run project.
Okay, now we need to dedicate some significant time to the license structure, because this project uses a very unique, and I'd say strategic, combination of licenses. The bulk of the system is licensed under the strong copyleft of the GNU Afro General Public License v3.0, the AGPL.
AGPL 3.0 is a very deliberate choice for projects that interact over a network, which the system does via its worker service HTTP API.
And the implication of that license is profound, isn't it?
It is. While users are absolutely free to use, modify, and distribute the software internally, the AGPL closes what's often called the network access loophole.
Can you explain that loophole and how AGPL 3.0 addresses it?
Sure. Traditionally, with a regular GPL license, you only have to distribute your source code if you distribute the binary. But if you take that modified software and use it to power a service over a network like a SaaS platform, you don't technically distribute the binary, so you can avoid the source code requirement.
I see.
AGPL 3.0 specifically mandates that if you modify Claude-Mem and you deploy that modified version on a network server where users interact with it, you must make the source code of your modifications available to those network users.
So it's designed to ensure that any improvements made to the core plugin framework, especially if they're used in a commercial or proprietary networked environment, are funneled back into the community ecosystem.
Everyone. But here is where the licensing strategy becomes truly complex and fascinating. There is a major exception noted for the ragtime directory.
A ragtime directory. This likely holds the innovative core retrieval augmented generation logic, right?
I would assume so.
And it's licensed separately under the Polyform Non-Commercial License 1.0.0. This is a dramatic legal carve-out. Why would they do this? Why impose this restriction on the intellectual core of the project?
This is a brilliant strategic maneuver. It speaks directly to the economics of open source R&D. The developers want the plugin architecture and framework to be open, that's the AGPL, which encourages contribution. However, they are protecting their key innovation, the RA engine itself, from direct, unregulated commercial exploitation.
So if a company wanted to take the core memory retrieval algorithms within that ragtime directory and just incorporate them into a competing commercial AI agent product, they would be barred from doing so.
Not without negotiating a separate commercial license, no. The Polyform non-commercial license strictly limits the use of that subdirectory to personal projects, academic research, or internal non-revenue generating applications.
So it's a protective measure.
It is. It allows the community to study, understand, and even modify the RA engine for non-commercial purposes, which ensures transparency and educational value. But it prevents competitors from cannibalizing the most technologically advanced and proprietary part of the system for immediate financial gain.
This balance highlights a critical tension in modern open source development, doesn't it? You want community contribution and scrutiny,
Which is the AGPL part.
but you also need to protect your specific R&D investment and maintain a potential commercialization path for your highest value IP.
Which is the Polyform part. The combined license structure ensures that the plugin framework remains maximally open, but the innovation driving the efficiency, the RAG core, is safeguarded. It shows a really sophisticated understanding of both community dynamics and intellectual property strategy in the competitive AI agent space.
That distinction between the framework license and the RAG core license is one of the most significant insights for any learner looking at the economics of open source AI tools today. Hashtag ad outro.
So we started this deep dive with the problem of AI amnesia, and we've concluded with the architectural brilliance of Claude-Mem. Let's try and synthesize the core takeaways one last time.
I think we learned that Claude-Mem achieves LLM memory persistence using a robust, highly performant worker service managed by the Bun runtime. It offers real-time visibility through an HTTP API. And that persistence is built on a hybrid database strategy. It's combining the high-speed keyword search of SQLite with FTS5.
And the semantic depth of the Chroma vector database.
But the true ingenuity, I think, lies in the economic efficiency of that three-layer workflow and the philosophy of progressive disclosure.
Right. By constraining the agent with that important system prompt to use search, then timeline, and only then get observations, the system achieves an estimated 10x token savings.
All by filtering context before authorizing that costly full detail retrieval.
And the implementation is just frictionless for the user. It simplifies all these complex dependencies through automatic installation and provides robust control via that settings.json file.
And it all exists within an active community, but with a strategic dual licensing model, AGPL for the framework, Polyform for the core RAG engine, to encourage collaboration while protecting that key innovation. We've explored how this system really monitors biological long-term memory. It doesn't recall everything, but it recalls specific, compressed, and semantically relevant lessons right when prompted. And this raises a really important question for the future of development.
If AI agents can now possess this highly optimized, project-specific, persistent institutional memory, how profoundly will this redefine the concept of a new developer joining a team? In the future, when a human or an AI agent joins a project, they won't need weeks to ramp up. They'll just instantly connect to a compressed, searchable, semantic history of every successful fix, every architectural decision, and every technical constraint documented by the previous agents.
This instantaneous transfer of project knowledge could fundamentally dismantle the traditional ramp-up curve.
And change the very definition of institutional coding knowledge altogether.
A knowledge base that never truly forgets and it's instantly accessible. That is the future of development we are now entering.